appreciate you guys for your likes and your comments on our last video that we did, and I promised you guys that in our next video we'll be channeling all our attention or all our energy to calculations for today. So on this very note, I will want you to stay tuned, relax, and keep your eyes fixed on your phone or your system or whatever device you're using to watch me on my YouTube channel, so that you will not miss anything at all. Alright, so we can start. Now, our heading for today is calculation on gases law, as you can see on the board. So we'll be solving different calculations in all of the gases law that you know and that I was able to teach you guys in our last video that we did. So the first on my on the board is this. The question says, calculate the pressure necessary to compress isothermally a 105 dm³ sample of air at 1 atm to 35 dm³. Now, when you see a question given to you, the first thing you do is to bring out all your parameters. It is your parameters that will tell you the formulas you have to make use of. Now, it said calculate the pressure necessary to compress isothermally a 105 dm³. It means given to me in the question is the V1, which is 105 dm³, sample of air at 1 atm, meaning the P1 is 1 atm, to 35 dm³, which is the V2, 35 dm³. I was asked to look for the pressure, which is question mark. Now remember that when you hear of the word isothermal, it means, now when you hear of the word isothermally, it simply means that your delta T is equal to the, meaning your change in temperature is constant. So indirectly it is telling me about what the Boyle's law, which says that the volume of a fixed mass of a gas is inversely proportional to its pressure, provided the temperature will remain constant. So from Boyle's law, we are aware that V1 P1 is equal to V2 P2. Now in the question, I am looking for my word V2. Is that clear? Now it means that P2 is equal to V1 P1 over what? V2. So we solve. My V1 is 105 times my P1 is 1 all over what? My V2, which is what? 35. When I do the calculation, I will get my pressure to be 3 atm. Is that clear? Alright. So we move. Okay, we are now to the next question, which is question 2. So to what temperature must a sample of oxygen, which has a volume of 800 cm³, as you can see on the board? So let's not waste time in reading too many questions. Already they are on the board, as you can see it on your phone screen. Now, how do we address such a question when given to you in the day of your exams or any relevant exams you have to write? Now we start to solve the question. Then which have the volume of 800, so it means given my volume V1 is what? 800 cm³ at 25 degrees Celsius, which is my T1, 25 degrees Celsius. Remember, you were told that in gases law, all your temperature in degrees Celsius must be converted to absolute temperature in Kelvin scale. So it means, and to do that, you add what? 273 to your what? Degree Celsius, which is plus 273, which will give me 298 what Kelvin. Now we move to say for it to occupy a volume of, meaning the V2 here is equal to 300 cm3. So it then falls back to the initial starting of the question. Now, to what temperature must a sample of oxygen which has the volume of 800 cm3 at 25 degrees Celsius be cooled, and so on. So it means my T2 is what I am looking for. And such a question with all the parameters given to you in the question, it means that we are talking about what? Sharp's law, which states that the volume of a fixed mass of a gas is directly proportional to what? To its temperature in Kelvin scale, in Kelvin, provided the pressure remain constant. So if I'm to invoke the Sharp's law, which is from Sharp's law, V1 over T1 is equal to V2 over what? T2. And from the question, I am looking for my what? T2, so that my T2 becomes, I cross multiply V1 times T2, T1 times V2. Because I am looking for my T2, I'll make T2 the subject of the formula. So it therefore means that T2 is equal to T1 times V2 over V1, which is not equal to, my T1 here is 298 times my V2 here is 300 all over what? 800. So I guess I can clean here now. I guess I can clean. All right, I guess I can. So we continue. Now look at it. When you do all the calculation, 0 cancel 0, 0 cancel 0. So when you do it, you now have that your T2 is equal to what? 111.75 Kelvin. But I have told you that sometimes that you'll be asked to calculate your, or to leave your answer in degree Celsius. So what do you now do? You now say, remember that in getting your answer in degree Celsius, you are aware that that degree Celsius is equal to what now? Is Kelvin minus what? 273, right? So that my Kelvin here is 111.75 minus 273, which will now give me minus 161.25 degrees Celsius. So in any way you are asked to leave your answer, you leave your answer in either of these. Okay, all right. Okay, we move again to the next question. Please follow the way I am solving all the questions, because they are basic points. You see, we are moving from simplest to the most difficult question. The next question is like this. Say a gas sample in a container has a pressure of 2 atm at 25 degrees Celsius, so as the case may be. So look at it very well. Now let us solve. Now solution, you bring out what you were given. Say a gas sample has a container, a gas sample in a container has a pressure. Then the P1 here is 2 atm. Okay, the T1 here is at 25 degrees Celsius, which I have told you that you have to convert to what? Kelvin scale by adding 273 to give us 298 what? Kelvin. And I said if the temperature of the container rises to 90 degrees Celsius, what will be the pressure? Meaning I am looking for the P2, while my T2 was given to me to be 90 degrees Celsius, which in converting to Kelvin scale, you have 273 to it. Okay. So you get what? 363 Kelvin. So this question falls under what we call the what now? It falls under the Gay-Lussac law, which states that at constant what volume, the pressure of a fixed mass of a gas is directly proportional to what? To its temperature. So it means if I'm to apply the use of Gay-Lussac law, I'll be having P1 over T1 is equal to P2 over T2. Now I'm looking for my P2. I'll make P2 the subject of the formula. So P2 is now equal to P1 multiplied by the T2 over what now? The T1. So that the P1 here is 2 multiplied by the T2 here, which is 363 all over the T1 which is 298, and that will give us our final answer to give us 2 point, okay, that's you multiply, then you multiply, then you divide 2.436 ATM. So we move straight away to the next. We move straight away to the next question, which is question number 4 to solve. Now, if you look at this question, it falls swiftly on what we call Graham's law of diffusion. Okay, let's solve. So solution. Now, the rate of diffusion of an unknown gas was determined to be 2.92 times greater than that of ammonia. What is the approximate molecular mass of the unknown gas? Please be very, very careful. Whatever we are solving here or we are doing here applies to all questions. So it is for you to read, understand, then apply it to any calculations you are to see. So we move swiftly. So, and you are aware that from Graham's law of diffusion, the rate, if I'm working with two more figures, let's say A and B, so it means the rate of diffusion of A over the rate of diffusion of B is equal to the square root of the molar mass of B over the molar mass of what now? Of A. Shortcut. So with this we can apply it. Now in this question you are making use of the rate of diffusion of an unknown gas. Let's say that the unknown gas is X. So it becomes RX over why that of the rate of the ammonia has to be ammonia is equal to the, now the square root here. Now the molar mass of ammonia here, see the molar mass of ammonia all over the molar mass of the unknown gas X. So I can now solve. Now if we should clean the board to progress, so we bring out what we were given. We bring out what we were given. We're giving the rate of diffusion of the, which they said, look at, they said the rate of diffusion of an unknown gas was determined to be 2.92 times greater than that of ammonia. It means here will be 2.92, while that of the ammonia will be equal to, since they said it is greater than that of ammonia, so here becomes 1. Is that clear? So that we are looking for the molar mass of the unknown gas, while that of the molar mass of ammonia is equal to nitrogen is 14 plus hydrogen is 1, which is the ROM of hydrogen is 1, multiplied by 3, so you'll be having 14 plus 3, which is equal to 17 grams per mole. So we have to bring out this calculation. So we now be having 2.92 over 1 is equal to the square root of ammonia is 17 over why that of the gas is what I'm looking for. Is that clear? So we quickly progress. Now equal to, now if in such question like this I'm looking for what is in this square root, so what do? I will stay to square both sides, so that square roots cancel, so a square cancel square roots. So I'm now having 2.92 is equal to 17 over x. Now if I'm looking for x is not equal to, I cross multiply, x is not equal to 17 over 2.92, which is now equal to, alright, so that the answer becomes what? 1.99. Exactly. Now, please be very, very observant. I know where some of you we tend to have problem with this aspect. Please let me explain this part again. That the rate of effusion of an unknown gas was determined to be 2.92 times greater than that of ammonia. It means that the rate of effusion of the unknown gas is 2.92 times greater than that of ammonia. It means in such a question, you put the value to be the rate of the effusion of the unknown gas to be 2.92, while the rate of that of ammonia is 1, because this one is greater than that of ammonia. There are many ways to solve such a question, but I believe that the easiest way that you can use to solve such a question is what you are seeing here, which is very, very clear to you. So we can move ahead to the next question. Okay. Now, this is another question again, but this one is now more matured than the ones we have been solving, so you have to pay keen attention to what we are doing. Now, they said a chemist vaporized a liquid compound and determined its density. If the density of the vapor at 90 degrees Celsius, so you can, if you read through the question, you understand it. Now, let us bring out the parameters we were given. First, we were given the density to be 1.58 gram or 1.58 gram per liter. We're then giving the temperature, which is 90 degrees, which we have already converted to what? To Kelvin. Then we're giving the pressure. Remember, I have told you that pressure is always in millimeter per mercury in atmosphere, and as the case may be. But I have told you, because of this gas constant, remember, you should know that when the question is given to you, from the parameters you are given, you should know vividly well that the gas constant R must be what? 0.0821 atm liter per mole per Kelvin. Please be very, very observant and conscious that all your units that are given to you must be in this appropriate unit that you are seeing here, atm. And here you are giving your what? Milliliter mercury. So it means you have to convert this from milliliter mercury to what? atm by what? By dividing by 760. Remember, I have told you that 1 atm is equal to what now? Is equal to 760 millimeter mercury. So if I have to convert this one here to atm, what do you divide by 760? Which, if you should do, you will have what? 0.9907 atm. So we solve. Now you are aware that I have in our last block of lecture, I told you about the relationship between density and the ideal gas what equation. Exactly, which is PM is equal to dRT. The pressure, the molar mass, the density, the gas constant, and the temperature. And from here, I am looking for what? The molar mass, whereby the molar mass is now equal to dRT over what now? Over P. What's my density here? 1.585. What's my gas constant? 0.0821 times my temperature, which is 363, all over my pressure is 0.99079. All right, which is now equal to, okay, which our answers approximately we give when you multiply and you divide, we should get 47.7 what gram per mole respectively. So we move ahead to the next question here immediately. Okay, this is another question which is solution. Let us solve it. Now they said the density of oxygen is 1.43, which you are seeing on the board. They said at STP. Remember, when you have the word at STP, it simply means standard temperature and pressure. First of all, determine the density of oxygen at 70 degrees Celsius and 800 watt torr. Now this question, now there's a little twist. How come they gave you density and they ask you to correct for the density? So it means you have to remove your eye from this one you are giving and focus on the question. So determine the density, which is I'm looking for my density. Okay, and I was given my temperature, which is 17 degrees Celsius, which I'll convert to what? To Kelvin. And again too, my pressure was given to me, which is 800 what? Torr, which I will convert to what now? ATM. Remember that 800, that 1 ATM is also equal to what? 760 Torr, as in the case of that of what? Millimeter what? Mercury. So it means 800 over what now? 760 what? Torr. Now our gas constant is always R is equal to 0.0821 ATM per liter per mole per Kelvin. So, all right, go. So you see that the temperature is now 290 Kelvin, while that of the pressure is 1.053 ATM. So if you should apply the formula that we have applied there, we'll be having PM is DRT. Now I'm looking for my density here. So density D is equal to PM over what? RT. Now my pressure here is 1.053 multiplied by the molar mass of oxygen. The molar mass of oxygen. Remember, oxygen is a gas, and at room temperature is O2, which is oxygen molecule O2. So it means if the ROAM of oxygen is 16, we have to multiply it by 2, which is 16 times 2 is 32 grams per mole. So here becomes for 32 over the gas percentage is 0.0821 multiplied by the temperature, which is 290. When you multiply and you divide, you should get your final answer to be what now? Approximately should have to be 1.42 grams per liter. All right. Fire. So on the board is another question again that will also address this address. Now this is the question. The question says, from the kinetic theory, the expression for the ideal gas pressure is derived as follows. Please take note. In the derivation of the expression of the ideal gas pressure, this is the basics of the formula, which is PV is equal to 1 over 3 Nm per Nm then Basi square, which I'll tell you the meaning of what they are. So it means if you are looking for the pressure, it even means that the pressure P now will not be equal, just divide both sides by V. So you'll be having what now? You'll be having Nm over what now? 3V, and the unit is in what now? Is in dynes per centimeter or square. Now the question that you will now ask is, what is, look at it, it is from this formula you are seeing there that they derived nearly all the laws, all the Boyle's law, the Chance law, and in fact this is the basis of the ideal gas equation. Now what does this N stands for? What does the M stand for? What does the Basi square that I called for you stand for? Of course, you are aware that this was a formula to you, the pressure, the volume. Now, N stands for number of molecules. Some tests will tell you small letter N, which is number of moles. You are still correct. Why this M stands for the mass? Why this Basi square stands for the what? The mean square velocity. Is that clear? So in case you are asked such a question, or you are working on a project like this, so this is what you have to make use of that. The pressure is equal to the capital letter N M Basi square over 3V, and I've just told you what each of these parameters they represent. Is that clear? Now we now move straight away to the next question. So I'll move on to the next question here. It said, calculate the final Celsius temperature required to change 10 liters of helium at 100 Kelvin and 0.150 atm to 30 liters at this one. So we bring out what we were given solution. Now we were given the volume V1 to be what? 10 liter. We're given the T1 to be 100 Kelvin. We're giving the P1 to be what? 0.150 atm. We're giving the V2 to be 30 liter. We're giving the P2 0.2 atm, and we're asked to look for the T2. So that this question falls under what we call the combined gas equation, or the general gas law, which is V1 P1 over T1 equal to V2 P2 over our T2. I'm looking for my T2. So it means that my T2 is equal to, I'll make T2 the solid of the formula. So by making T2 the solid of the formula, I'll be having it to be T1 V2 P2 over what now? Over my V1 and P1. My T1 here is 100 Kelvin multiplied by my V2 here is 30, my P2 here is 0.20, all over my V1 is 10 multiplied by my P1 is 0.150. When you multiply and divide, all right, we have our answers to be 400 Kelvin. But remember that the question had told us that we should leave our answer in what? In degree, in Celsius or temperature. So you are aware that in Celsius, now you'll be having degree Celsius is equal to Kelvin minus what now? 270, which is 400 minus what? 270, which is equal to 127 degrees Celsius. So that's the final answer. I hope it's clear from the way I brought them out from the question. I brought them out, then I apply the general gas law, which is what you are seeing here. Then I made this one the solid of the formula. Then I did all the calculations by multiplying and getting my 400 Kelvin. Then converted, and then I converted it to degrees Celsius. So move ahead to the next question, which is just down. All right. Now, as the question goes, you can see here. Now we can now solve. Now, from the question, we're given our volume to be what? 5 liters. We're given our temperature from the question that you just saw to be 18 degrees Celsius, which we converted to Kelvin to be 291 Kelvin, and we have to look for the pressure. Now, this is one question that you must be this is one aspect that you must be very conscious of. Now, our number of mole of hydrogen gas was given to us to be in mole, but that of the CO2 was not given to us. Rather, we're giving the mass, which I have told you, you have to convert this mass to mole by what divided by the molar mass, and the molar mass of CO2 is 44. How? The RAM of carbon is 12, oxygen is 16. 6 times 2 is 32 plus 12 gives 44. So which way you divide, you get this value. Now, that of the oxygen gas was also the same. So we should also convert the mass to number of mole by saying 14 divided by what? 32 should give us this. Now, because of what the formula implies, which is PV is equal to nRT. So it means there is need for me to calculate the number of moles, the total number of moles of it by what? Adding each of them together, which is 0.2 plus 0.455 plus 0.4375, which should now be equal to 1.0925 mole. I hope it's clear. Now, since I'm looking for the pressure, I'll make the pressure the subject of the formula, which will now be P is equal to nRT over what? V. The number of mole here is 1.0925 multiplied by 0.0825 times my temperature, which was given to me to be what now? 291 all over. The volume here is what? 5. Which when you multiply and divide, you get your final answer to be, and our answer is 5.22 ATM. Alright, please go through the question again and go through the answers again so that you'll be so clear on how they are being gotten. So we can move to the next question. Alright. Now, looking at this next question, they said what you can see the question there that the volume will be. So now, solution, as we have always been doing, you bring out what you are given. You will ask to look for the volume, you are given the mass, you are given the pressure in torr, which you have to convert to ATM because of the formula we have to make use of, which is the ideal gas equation, which is PV is equal to nRT. Exactly. So we will convert this torr to ATM. You divide by 760. This is what you have. Now you also get the number of moles. So we're given the mass. So to convert this mass to mole, it's divided by the molar mass of what? SO2, which is 64. And you have seen the way we got it here. Now we have a value to be 0.019 mole. Now we're looking for the volume. So volume V will now be equal to nRT over what now? P. Now the number of mole that we had was 0.019 multiplied by our gas constant is 0.0821 multiplied by our temperature is what now? Our temperature given to us was 18 degrees plus 273, which will now give us 8 plus 3 is 11.1 Kelvin. Then we have our 2 plus 1, which is 9, which is 9. 9. Then we for that one we have O. Then it is 301 Kelvin. So which will set by 301. Then we divide by the pressure. Pressure gives us 0.993. So when you multiply and divide, okay, 291 Kelvin. So our final value will now be 0.4571 watts liter. So that's our final answer for 1. So we move swiftly to the next question. So in this next question, we'll stop swiftly on this next question, which is, as you can see on the board, this one falls under Dalton's law of partial pressure, a sample of oxygen as the case may be. Now, solution. Now, observe the vapor pressure of water at 25 degrees Celsius was what now? Was 24 torr. So it means that this pressure given to us was for the total pressure. Now, immediately it was collected over water, the pressure of the gas will now be decreased than the original one, which is total pressure. So you are aware that from this formula, I give to the other one that the total pressure is equal to the partial pressure of oxygen minus what? The saturated vapor pressure. Now, if I'm looking for the partial pressure of oxygen, so it will now be, I'll make it the what? The subject of the formula, which will now be partial pressure of oxygen is equal to the PT minus what? The P the partial pressure of the water, which will now be 756 minus 24, which will give me what? 732 torr. All right. Now, from the parameters, from the question, we draft out these parameters, whereby the P1 now of the oxygen is what we are having here. Now, the V1 is what you are having here. Then the T1, which was given to us from the question to be 25 degrees Celsius, was converted to Kelvin to be 298. But remember, they said something. They said, what volume of the dry oxygen at STP? So it means my P2 will become this standard pressure, which is 760 torr. My T2 will become my standard temperature, which is 273 Kelvin. Now, the volume, the V2, which is the volume of the dry oxygen, is what we are now looking for. And this falls under what we call, we can then use the general gas law to solve such a question, which is V1 P1 over T1 is equal to V2 P2 over what? T2. So if we are making V2 the subject of the formula, we can therefore have that V2 is equal to V cross multiply V1 P1 T2 over what now? T1 or P2. And what's my V1? My V1 is 370, my P1 is what? 732, and my T2 is 273, all over my T1 is 298 multiplied by my what now? By my P2, which is 760 torr. Alright. So when we multiply, we divide, we tend to get one to be 326 cubic what? Centimeter. So I hope it is clear from this part to this part. This method of solving questions all applies to all questions that fall under Dalton's law of partial pressure down to the combined gas law. So as the case may be, you will see how all the steps are followed sequentially. All right. So we are now getting close to the end of our questions for this part, and the questions are like this. So calculate the ratio of the efficient rates of hydrogen gas and uranium metafluoride, and these are the molar masses which is very easy to calculate. If hydrogen is 1 multiplied by 2, you have this one. If uranium and that of the fluorine. So you are aware that the rate of diffusion of hydrogen over the rate of diffusion, so the rate of effusion of UFC, molar mass of uranium metafluoride over the molar mass of hydrogen gas. So if we are to solve for it, we are having the rate of effusion of hydrogen gas over the rate of effusion of uranium hexafluoride. The molar mass given to us, the molar mass that we know is 352O2, and that of the hydrogen to be 2.016. So that when you divide and get the square root, you're having 13.2. So it simply means that approximately that the rate of effusion of hydrogen gas is 30 times that of uranium hexafluoride. So, and this brings us to the end of today's blocks of lecture. When next we do our next video, we'll talk more on the molecular speed of gases and Van der Waals equation, which I would like every one of you to please click and like and subscribe to our video to get more updates. Please I love you all. My name remains Adrenaline, the Bazooka Prophet.